And in my estimation, he's one of the really bright people in mathematics and science education. I'll claim him in mathematics education because he's done a lot of work in mathematics education. His actual, his undergraduate degree was in biology and physics. No, chemistry. Biology and chemistry. And then he did his work at university I guess it was at Albany, and in educational psychology and statistics. So he tells me he keeps that his chemistry mathematics education was at the University of Wisconsin, where he was at faculty member for 18 years. And he got working with the math educators there, and statistics, he tells me. And so he done a lot of work on children's spatial concepts. And he was doing a lot of work on that. And now he's working with Leo Shell on statistical reasoning. And I don't know whether that comes out all the time yet.
No, we were making a hash of this all on our own.
So it is my great honor to introduce this because he's really one of the outstanding researchers, I guess, in science education and also on mathematics education.
Thank you, Les. Thank you for the invitation. Ron asked me to talk about learning progressions, so that's what I'm going to spend some time talking about. Unfortunately, I can't talk about a finished learning progression, but I can talk about a work in progress. So I'm just going to share with you some of the things that we've had to think about in order to try to articulate a learning progression. And I want to first acknowledge my colleagues in crime. There's the Berkeley Evaluation and Research Center, that's Mark Wilson. And there's also a group of teachers in a cooperative in Northwest Arkansas where we've been doing a lot of our work in assessment and professional development. So what I think we have to first acknowledge is if we're going to develop a learning progression, we're really talking about three interlocking systems. You need to have some model of progress in learning and what that would entail. You need to have some system of formative and summative assessment, and then a program of professional development that's going to orient teachers to the model of learning and to productive uses of assessments as tools for learning. So that's really what I'm going to be sharing with you today. From my perspective as a person interested in not only mathematics but also science education, the need to develop the ability to reason statistically is very simple. You can't engage in science without it, unless people are going to very conveniently arrange natural systems with non-overlapping distributions. Otherwise, as soon as you, which they do all the time in school, but if you want children or students to be able to pursue their own questions, then they need some way of reasoning about variability and uncertainty. You just can't get away with it. So the design problem that we're facing is that the current practice in statistics is not knowledge in pieces, but instruction in pieces. And I think we're all familiar with this. As you know, there are only three ways to represent data. Usually data are given, they're not generated by a process that you participate in. A statistic is something that you do it to the data. I have lots of students who come in and as soon as they see a batch of data, they calculate a mean. Doesn't matter if there's any question. And chance is a separate topic. It floats off over here somewhere. And what inference has to do with any of these things is anyone's guess. And that, I think, is, of course there are exceptions, but that's the canonical practice. So our response to this is to think about statistical reasoning as embedded within a process of what we call the data modeling. And it starts out with the idea that you really want to answer a question. And to answer a question about some natural system, you need to think about, well, what attributes am I going to pay attention to about that system? Because they're usually complicated and not many things you could pay attention to. What should you pay attention to in relation to your question? And then, if you want to attend to those attributes, how are you going to measure them? And I don't want to get off on a tangent here, but often the very act of measuring establishes that actually you're interested in some other attributes, or that your understanding of those attributes changes. So I just see that as a dialectic all the time. Let's say we were satisfied with our measures, and we've done that work, and we start collecting measures. Well, now we have problems of structuring and representing those measures. How are we going to describe the distribution of measure? We call those measures statistics. And then really what we want to do is account or develop ideas about this batch as having something to do with chance. So we need to be able to develop models of chance in relation to the data that we've collected. And putting all those things together allows us to make an inference that we call statistical, that makes explicit, takes into account chance. So that's what we're interested in. That's our guiding vision of statistics education for kids. Now, it doesn't start out in full-blown things. So these are first graders who have answered a question about how do they wake up in the morning. And those are post-it notes that are put up on the blackboard. And the question is, can we organize them in a way that would allow somebody else walking in the room to see how we wake up in the morning? So we try different things, and you can see that our dominant way of waking up is we've got parents that are very thoughtful. And we go through these various ideas of restructuring the data and what that shows and hides about the data. This is from a first grade investigation, fruit fly escape. So we're trying to develop a model system to understand rot. We've been looking at tomatoes rotting in the schoolyard for some time, but then it's what's happening. So what happens in October, at least at the time of this study? Freeze, so everything gets arrested. So how can we keep studying this? So we have to decide how to import this into a classroom. What is it about that rot that we're going to preserve? Do we keep the styrofoam in or not? You know, the school ground isn't always it's sometimes not all that tidy. So we're looking at rot in the compost columns. And we don't know this, but there are unwanted guests. Some critters have laid eggs in the stuff that we've brought in. And these critters are fruit flies. And they find this rich source of now decomposing materials, very conducive environments. So we launch into a little study of fruit flies, but the problem is the fruit flies escape. And so we go around and take a little census of where the fruit flies are. This is a map of our school. The origin classroom is here, and these classrooms are easily explained, neighborhoods. But what about this, and why not here and there? So it turns out that some classrooms have more resources for fruit flies than others. And what we like about this is that it's a display-based question. So we're putting our representation to use. Same kinds of things. Here's a second grade class, and you can tell that this might have been, at the time, a more rural community, because when given the choice in a children's story about where they want to live, most of the students want to live in the wide country. They've heard bad things about those tall cities. And so these are links that are put up in front, and they just add a link as to what they would prefer. And then their teacher challenges them to re-represent that, again, so that someone else just coming in could take a look. And these are the kinds of things that go on as the kids try to think about how to coordinate space and quantity so that we can communicate. And so we have these discussions about whether or not spatial intervals should be alike or different, and so on. So that goes on, and we publish something with our teachers in Teachers College Press about these kinds of things. And we continue to engage in this kind of thing. I'm not going to go through this example because I'm looking at the time, but it has to do with a unit, social studies unit on silkworms and their role in the economies of China and Korea or Japan, I forget. But the kids decide that what they want to do is import these critters and grow them. And so these are examinations at a day of growth of a measure of their length. And the kids are challenged to invent displays. And there are 163 of these things, so it's actually a significant challenge. There's all kinds of debates about what you can see and what you can't see in the displays, and so on. There is, again, display-based inference. They want to know, like, why the tails are sparse, and most of the organisms are found in the center of their displays. And we also try to do some work linking ideas of chance to these forms of science investigation. This is from a 3rd grade class. They have conjectures about where crayfish are going to live. They've altered the bottom of a wading pool, and they're doing observations about where the crayfish seem to be congregating. They have conjectures about this, and what we're trying to do is contrast it to a 4-sector spin, and what might we expect just by chance, and just to start to develop some intuitions about whether or not what they're seeing could be just as easily described by chance, or maybe there's something about the substrate that the crayfish prefer. So I want to talk today, though, about a learning progression for these ideas centered in grades 5 and 6. And so this work has the following components. First, we need design studies for trajectories of student learning. At the same time that we're conducting these learning studies, we need to design an assessment system, and I'll talk a little bit about that. That's work with our colleagues at Berkeley. We also need to design professional development, because while we're directly involved, it's easy to see what we should do next. We have all the kinds of conversations that we usually do in teaching studies, but what happens as you start to move it to other people not involved in the original design. I'm going to culminate with a design experiment, which is ongoing now, and I'm going to conclude with a notion of a learning progression as a training zone after Gallison's work in social studies of science. But I'll talk a little bit more about that. Okay, so with Cliff Knoll, we've been thinking about, well, what are good contexts to investigate variability? And we've been thinking about 3 of them: repeated measures, manufacturing, and naturally occurring things. Now, if we have a context of repeated measure, we have a single measurement, and we have some estimate of center where the actual measure resides. And then variability is produced by measurement error. So I think the way Cliff likes to say this is that this is a clear decomposition into signal and noise. And if we manufacture bolts, we have a similar decomposition. We know what it is we'd like to accomplish, and we know that we don't always get there. So we have a target, and we have variability, and that variability is usually due to variation in process. Heights of people, well, we have the height of a single person, and we have the height of many people, but what does center mean? We have naturally occurring variability, but where did it come from? So if we think about potential affordances of these contexts, we can see that we can generate distributions by measurement processes, manufacturing processes, or unobservable multi-system processes for natural variation. The signal is a true measure, or a target value, or some center of variability, if you're talking about species or some attribute of a whale. And then the potential visibility of the generators of the variability, depending, of course, upon the particular process. We're not living in a platonic world, but generally think it's pretty high visibility. You can see how the process of error might occur in measure. You can see variations in manufacturing processes. And it's pretty hard to see the biotic and abiotic processes that result in natural variability at work. Of course, we can instrument and do that, but we're just talking about initial access here. So, with that in mind, we engage in design studies. And these feature multiple cycles of design and vary in distance from the original designers. The first set of designs are in an urban middle school, grades 5 and 6, and we did the typical kinds of things one would do. We had individual clinical interviews, field notes, video recordings of whole group and small group conversations. And we replicated the design in a suburban, rural middle school in a different state with 4 classes. I taught one of the classes, I co-taught the other class with the teacher, and then the teacher taught the last 2. So we did that for a while. And then we went to Northwest Arkansas, and that's just personal serendipity, I wound up there, and worked with 29 teachers. And with those teachers, we really did a lot of the work developing the assessment system. There was also another opportunity to see the travel of the design and where the challenges might be. So let's embark on our trajectory. So given our analysis, it makes sense to start with repeated measure. So everyone's going to measure the same thing, and keep it simple, something like an arm length, a head circumference, or we can use our ray guns and some trig and get the height of something. The key thing is that the process is based upon individual agency. You can do these things and think about them. And we always switch the tools, because what we're trying to do is change the variability. And again, help people explain changes in variability as changes in process. So every time we do this, we try to think about, well, what are the resources that students are bringing to bear? So the first is a theory of measure. And I put a C there to denote that that's a constructed resource. That is, before embarking on this, we engage students in thinking about the nature of units and scales. And we put that stuff to use. So they come to this with some notion about what measure is. Now, as we move the design out, that doesn't always work. So it's questionable whether or not measure is really a resource all the time. The second is the notion of agency, just that you can engage in the process, as I mentioned before. The third is the goal is very simple. Like, how long is that? The fourth is that people notice differences. And the fifth is that a collective, that is a distribution, emerges from individual activity. So we think of all of these things as resources brought to bear. And the problematic that we're engaging is that, somewhat to many students' surprise, the measures are variable. So they don't all come up with the same measurement. In fact, some of them are wildly different. So what we're conjecturing is that this repeated measure context is going to support a coordination of data and process, and that what will help this is the variation in the process and the method of measure to be able to see this. So that's our initial grounding. We involve students in the collection of data to answer this question. Then what we want to do is problematize the shape of the data. We don't want students to think that shape is something imported, but rather that it results from the choices that designers made. So we asked students to invent displays, again, as you saw earlier, that would show somebody just walking in the room something that they've noticed about the data, some pattern, whatever they would like to do. And our problematic here is that what we're counting on is that their solutions will vary. And in fact, to the teacher's astonishment, they do. And all that talk they've had about graphing for 5 years doesn't mean anything. You'll hardly see it. So we expect that they'll be able to look and detect patterns, that they are familiar with technologies of paper, and that we're going to have, that they have some kind of conversational norms. Because the second part of this is to make the functions of measure visible collectively. Because one of the ways you figure out a system of measurement is collectively. Because you have to be able to communicate your measure and people have to be able to judge its adequacy. So measures are not just an individual activity. Oh, but on the slide ahead. If you look at me, why are you talking about measurements? I don't know. But same thing for displays, whatever I said. Okay, so here's what you get. In some class, this is an unusual response, but I loved it. This pair of students said, the problem with you people is, you obviously have been on too many pharmaceuticals or something. There's absolutely no pattern in this measure, because you can't reproduce it exactly. So that's not what we call a mathematical pattern. So go away. And it kind of ignited an interesting conversation in the class. Many students look at these collections of data and order them. So we get displays that look like these. Some have counterparts in case value displays. Others are just lists or staircases or whatever. But the big thing is they're attending to order. Some students attend to frequency. They often don't think too much about the interval, but they'll attend to frequency. And if you can see in this one, this was done by some middle school students who knew that you're supposed to calculate statistics when you see a batch. So they did. None of them are right, but they're all there. Something to organize and into classes. And of course, makes perfect sense. You put the most frequent class on the left.
Until I got to the 130s.
Some attend to frequency and interval by thinking about what's missing. Some use some imported other devices like number lines to think about intervals. And some put these things together. But this is the kind of variability that we see typically. So that gives us a great opportunity. And that opportunity we try to exploit in this collective activity structure, which we call a display review. So what we do is very simple. We look at pairs of displays, and we think about what each one shows and hides. And generally, a student who didn't create the display is the presenter of the display. And we talk about what the designer did to make it look that way. So we're trying to develop notions of how we coordinate things like count, order, frequency, intervals, to create displays and what implications those have for how they look. So after we go through those things, and we've had those conversations, students can use the displays they created or anyone else's. And we now pose the question of, well, how would you measure the length, or how would you measure the precision with which we measure this attribute? So we ask students to invent measures. Now, resources here are their theories of measure again. It really helps if they have a theory of measure and think about what measures should do. The shape of the data from the display activity they just completed. Some notion of algorithm, although it's usually tacit, but the notion of reproducibility of results, reproducibility of methods of measure. And at some point we introduce Cliff Knoll's tool, take the class. The problematic that all measurers face is what does the structure, the symbolic structure of the measure have to do with the characteristics of the phenomenon that's being measured. And here, what we're talking about are measures of distribution. Then, after rounds of invention, students participate in what we call a measure review. And here, the notion is that different measures are compared and contrasted, and students make judgments about whether or not the measure is good, and if so, what's it good for. Again, we're conjecturing that this variability is going to give us an opportunity to establish, first, what a statistic is, and secondly, how a statistic is a measure. So here are typical things that happen. Some students focus on repeated measures, and that is, say, a measure of the true value of the measurement. Others focus on centers in different ways, but often, at least in every class, someone will reproduce, either reproduce or come very close to the logic of a median. And the reason I put this here is that justification being offered here has to do with symmetry, and basically treating a center clump as a reflection line. And I say to her as well, I'm talking, oh, so you're using symmetry? And she looks at me and goes, well, not quite. It doesn't quite, so. But she said you could think of it as near symmetry. So I have from there. And then we have some that focus merely on distance, mid-ranges, and so on. In precision, we intentionally don't really define that, and we let the students try to engage in a conversation about what could be meant by precision, because that also kind of creates the need for thinking about, well, what is it that we're trying to measure? And generally we get to some notion of the tendency of the measures to agree. Working from that, we get three kinds of solutions, although more, of course, but three things that are reproducible. Focus again on repeated values, focus on distance, and a focus on clump. Those are the kinds of inventions that we often see. Here's a distance-based solution. They are using the median as the center. Now, other kids just try to do pairwise things, and there are big debates about whether we should use something in the center as a reference point, or if everything should be its own reference point, etc. So, I mean, all of this is a process. And then the notion is, well, is it a good measure? Well, some of these deviations, when we use what's called a crude tool, we have a 15-centimeter ruler. So you do a lot of that, versus a meter stick. And so that's, on the right is the meter stick, on the left is the 15-centimeter ruler.
So this is a measure of precision on the measurement, not.
Yes.
I'm just, they were asked to estimate the actual length, the actual arm span.
Yeah, the actual arm span is the measure of center.
Right, and now I thought you were talking about how sure they were about their measure of center, but you're talking more about.
No, I'm talking about the variability in the sense of how much do we tend to agree.
Right, okay, so not the variability of the not
the variability in the mean or median, no.
Not the sampling distribution.
Not yet.
Okay, that would
no. These are just right now measures of static samples. Yeah.
Okay.
You know, some way in which, well, okay.
I just wanted to be honest.
No, yeah, that's right. Yeah. No, that's right. Yeah.
Could you just give me some sense of the way in which some of the distances arose in the population?
Say that again, less sorry.
In what way, give me some sense of the ways in which this measure, some of the distance from each measurement to the median, how did that arise in the group of students?
Some students spontaneously thought to compare. And the way it arises is that you could see the center clump. So remember the previous slide or two where she's like this? You know, it's in here. So once you get the notion it's in here, and if it's really here, then it makes some sense to want to know how far from here there is. So it's not something, but that's a typical pathway for that, but it's not something that we deliberately engineer, except that we think they actually do look a lot at center clumps.
So how would that be appropriate in our data students?
Okay, I'm going to get to appropriation. But first, we have to have another message from our sponsor, Sometimes when we problematize distance, the number in the samples, we start getting other solutions to this, finding the median of these differences so we can compare more readily across samples of different sizes. And some are center clump-based solutions, just looking at basically the width of the interval that contains their judgment of mid-50 or 78% or whatever. They say this is the center clump, and they can use divider tools on tinker plots to find that and say, so here is our measure. And they notice that when the measures are more precise, they tend to be tighter. So you'll have a greater percent in the same region. Because there are two different tools, so it's the same center. But here's the answer to your question. We have measure reviews. And in the measure reviews, the students present their measurements, and their qualities are talked about both by the presenters and by other students. And so here, we had someone who had a range statistic, and he says, look, if the measure is, if everything's completely precise, and this distribution doesn't exist, but it gestures like this, so they're all going to be stacked, and my value is 0. If they're all spread out, it could be some really large number. And this goes on, and other students say, yeah, but suppose, and then they create another transformation on the distributions that have the same range, but you can really see markedly different measures of compactness, or markedly different clusters in the center. So some are more spread out, some are tighter, and these are invented by students to test this statistic. So every statistic goes through this little process of basically an aesthetic of measure. So if a statistic is a measure, then there ought to be a correspondence of the scale to states of distribution. It should be generalizable, and you should be able to anticipate if the distribution changes somehow, what will happen to that statistic. And there's always contest about goodness of measure in light of what you're trying to measure. For example, there's really a lot of debate often about whether a non-existent value for a median can be said to represent the sample, because it doesn't exist. And the recourse that I've heard children develop about that, and with our little assistants, is always a possible value. It makes sense that if we did it again, so then that's good, right, because we want to get across this idea of a repeated process. Okay, so I'm going to run out of time, so I'm just going to say that, that we just continue along this path. We use tinker plots, and before tinker plots, handheld devices, not electronic devices, but literal things that we were spinning and throwing dice or whatever. And we explore chance, ideas about chance and mystery devices and what could they look like. And the only thing we know is we can look at their behavior, and if we have more of the behavior or less of the behavior, how confident can we be, and so on. We do those things. Sometimes kids get really interested in qualities of sampling distributions. So if we have samples of a spinner and we have it 10 times, and they look and see the sample variability versus 100 times versus 1,000, and this is directly from a paper of a fifth grader. Yeah, he was trying to help us out. He thought it was pretty stinking amazing. That was his when he introduced. So, and we thought it was too. So they developed some intuitions. We're not trying to formalize anything, but we're just trying to get them to play with these devices and notice and have some noticings about these things. Then what we engage them in is kids' analysis of variance. Because once we have our chance devices in hand, then we go back to measurement. And we say, hey, we got a weird idea for you. How much of this variability you think could have just happened by chance? And they're going, yeah, well, it used to be that they used to castigate individual measurers. That's why we don't put the ID on any of the measurements. Because this person out here was not careful. And this apparently is a sin in some places. So the notion that you can have variability arising from chance, that's an innovation. For many, models are not analogies, they're copies. And so this is another kind of challenge that we have to take on. And then if we had a model, how do we know it's any good? How do we start to think about model fit? So we start to model the measurements as essentially a fixed component and a random component, and the random component comes from the kid's analysis of the sources of error. And everyone knows what they are, but they haven't thought about trying to think about their likelihood or magnitude. So, so I'll just say that we do that. Here's a little part of a kid analysis, except we prettied it up. It did not look this good. We made a table out of it. This was in the early days before tinker plots when I was doing this. These were apogees of rockets, and those are spinners on these different sources of error. And one of the things that really socks the kids, that seems to provoke a lot of interest, is the idea that net error can be 0. So now, once we have control of this technology, we can start creating models. And we can compare modeled measurements to actual measurements. And we can start running the model again and again and again. So we start to develop the idea of sampling distribution. I should say that we have to have chances for evil along the way, because it's also good to think about how you build these systems. So we challenge them to make bad models. And I've learned that you can't just tell them to make a bad model, because one of our students had a spinner that said when you combined the sectors, it spelled Satan. I knew that we had to change these. So we challenged them to have about the same range and to try to change it to a V shape or whatever. And how would you change the model to do that? But that places us in the position for model-based inference, and that relies on an empirical sampling distribution. So we run the model again and again and again and again, and we say, okay, here's the model of this process. Now here's a new sample. So what do you think? Do you think it's from Mr. Rolfing, whose arm we measured in his other class? Or do you think this could be somebody else? And those are the kinds of games we play. So that's the culmination, as far as we get in this sequence. So now we have to design an assessment system. So working with our colleagues in Bayer, they said, okay, so what are the states of knowledge that you're interested in assessing? So we developed what they call construct maps. And that is, we have short summaries of forms of reasoning that we expect, and a kind of conjecture about their progression. And I don't want that to be confused with a learning performance. All it does, a learning progression, all it does is specify a state of outcomes. So if a model fits, that doesn't mean your learning progression, is validated. In fact, I'm going to argue that you can't do that. Nevertheless, we have these 6 constructs, and as you might have seen from, I'm sorry for the too quick blast through the last half of it, but we have ideas about display, representational competencies, conceptions of statistics, ideas about chance, how you would use chance to model variability, and then informal inference in light of chance. So these form a 6-dimensional space. Each one is a little bit more populated than what I just showed you, right? It has many more levels of performance for the most part. And the key thing is that we try to design items that tap, by student response, different levels of one or more constructs. Some items are multidimensional, some are unidimensional. But the notion is that we're trying to read student responses and locate them along the construct map. And Mark Wilson and his group do different kinds of psychometric modeling of this. We happen to be using multidimensional item response models. But some of the models we're using are latent class models. It just depends upon the question that we have. So we now have a system after 4 years of calibration with a couple of thousand students. And that's why we went to Northwest Arkansas and working with 29 teachers, because of course if you're not teaching students these things, they tend not to learn them. and then you can't measure them. Big surprise. So the kinds of things that we worry about for validity is whether or not item difficulty corresponds to levels of constructs. And if construct variability is all that we have to worry about, then item difficulty ought to flawlessly follow from where the student response is located on the construct map. Well, it's not flawless, but it mostly works. So we're pretty satisfied with this. I've seen some other things that people are presenting where I think we would be very satisfied. So this is, item difficulty has many sources, and construct relevant variance is only one. The second thing is we have these multiple dimensions. So is it true they really exist, or is it like, you know, we're just feverish? And in fact, all of this could be described by a single dimension, and we could all worry much less. But it turns out that there is a multidimensional structure. And the third thing we want to ask ourselves is, well, is it sensitive to change? Because if you can't track change with it, then it's obviously going to fail as a system to measure. So yes, it turns out we can. So these are the correlations in the multidimensional solution. Some are higher than others, but you know, all suggest that these constructs are related, and substantially so. That's a relief, they should be. But they're not the same thing, even from the model perspective. And it turns out that we can do pre-post gains, and so we just took one of the classrooms where that second design study I was talking about, where we had 4 replications, and we just said, okay, so pre-post is it sensitive? And is it sensitive in ways that make sense? So we're looking at relative magnitude of effects and so on. So in each case, yes, we can track change about student thinking and forms of student thinking that matter to us.
How do you get the negative scores on the pre-test?
Because they're centered at 0.
Oh, okay.
So does need IRT theta?
Yeah, it's IRT.
So there's a logic units.
Huh?
There's a logic units.
Oh, yeah. Now, okay, so the other thing we now have to think about is progression-centered professional development. And for that purpose, what we do is we treat the learning progression as tentative. So that is to say, we have these ideas, we have these conjectures, we've done a couple of design studies, some things seem to be reasonably robust, but now we have 29 new instantiations. So we involve teachers in helping us understand what parts of it are robust and what are not. They bring back samples of student work. We engage the teachers in modeling data because for most teachers, these ideas are new. Most teachers, you know, I mean, they need to be able to have a setting in order to make some conceptual progress. We try to design lessons that are educative, meaning that we try to reveal the purpose of the design, and we have samples of student thinking. I can show you some of those. We've created a video exemplar version of the construct maps so that, and populated with examples from me teaching, but also from these participating teachers. And the idea over time is to obliterate me and keep them. And we also work together. We piloted a lot of the items with their students, and together we look at student responses and try to think about whether or not they're meaningful. And often this led to a process of item revision. So these were all parts of our professional development. And we also did studies of the use of the items in formative assessment, because we want the items, some of the items, to be used as teaching tools. So Min Jung Kim, for her dissertation, followed 10 teachers, a few of them for 2 years. And she noticed a kind of a typical thing, a typical pattern. Initially, the students started out thinking about the items as right or wrong, which was very traditional. So all our labor about student responses and thinking and all that was not exploited. Then they started to have students present solutions, but the solutions were like this turn-taking structure, and nothing was done with them. Then they started selecting students to present based upon the construct map and its exemplification of a kind of reasoning in the construct map. And the highest thing that we saw were construct-centered comparisons. So there was deliberate effort to juxtapose different forms of reasoning. When we saw that, and we looked again in our system of assessment, this is a kind of thing that we would find. That when teachers were engaging in those comparisons, and we looked at the achievement of students in the classroom along with constructs, we would see pretty big differences compared to people kind of just starting out or on the road to their way up. So now we're in a position to do a design experiment. And our design experiment will be in 40 schools. There will be more than 80 teachers. The school will be the unit of random assignment. And for me, the interesting part about this is the issues of scale. And what's intellectually interesting about it is the reproduction of professional development. It's now led by the teachers who we were working with. We've included ideas about explicit rehearsal of what people in teacher education call high leverage practices. So how do you conduct a display or measure review conversation? How do you milk this thing for formative assessment for learning? So now we have that more or less, well, we're trying to study if we rehearse these things, if that will improve implementation in classrooms. And we also need a measure of treatment fidelity, but we won't have any idea if we find results what to attribute them to. So what we're doing is we're transforming the term structure. I mean, I didn't show you all those ugly analyses, but it goes on at some length, term by term. We're trying to transform the term structure into a measure. And so that work is being done by Seth Jones. Oh yeah, you can read that. Great. So, you know, oh yes, but he thoughtfully said, here, do it this way, Rich. Hang on. Break it into chunks. So, for example, if the students are inventing statistics and having a conversation about them, well, what kinds of conceptions of statistics are evident in the conversation? So we have these 5-minute samples, and we just try to note whether or not we see any of these things. So are they thinking about properties of a statistic as a measure? What kinds of statistics are they talking about? Student contributions. Do they actually share their methods? Do they make comments? Do they ask questions? And teacher practices. So we're trying with this measure to get some sense of what's going on in the classrooms as students are learning. And the other little sidestep here is back to natural systems. So if we do this kind of work and we're trying to figure out whether or not we can partition a pond ecology, whether or not different regions matter, well, maybe we can think about the null as it doesn't matter where you get the sample from, you throw them all in a hopper, and then we develop empirical sampling distributions of a certain sample size, and we say, okay, measure something like a count or a ratio of critters, and you think that could have just happened by chance, or is it something to do with the structure, the actual structure of the natural system? So we're trying to put this knowledge to use in sciences so that the students can actually engage in science. Thank you.
I'm sure you have comments and questions.
I have a question from the science perspective that I see missing here, or how you present here, is the students engage in discussion about the ontology of the object they're measuring. You know, in this case, say the Persian's arm span. They talk about what this thing is, you know, given the measurement activity they have.
Yes. in the sense that when they try to account for the variability of measure, there's a lot of discussion about, well, whether or not there's arm droop. And we actually have tapes and go across the muscles back here and see whether or not that changes, and so on. But I'm not trying to select things in which anything other than, oh, we get different responses, different measures, is at issue. So at this point, for students, the surprising thing is not that the thing has a measure, and it's not a particularly intricate measure, but rather that there's variability in the measure. And so that's really what I'm concerned about here. Now, if you're talking about measuring something in the pond, that's different, because that is a much more obscure place. And what would constitute a measure, and why would you measure, and what are your questions, that's much more involved. And that's a different talk of equal length, which I have. Anyone want? Yeah, so that's a really good point, but I'm just trying to say, I'm trying to be deliberately simple. Yeah, although every time you measure anything, you always get this, right? I mean, so droop, and can you imagine teachers get tired? A lot of teachers have taken to measuring perimeters of tables. But it is kind of fun when they, and of course I got my circumference of my head measured too. And when they used a 15-centimeter ruler, you see that crease? I think that's it. Well, just very simply, taking as a form of evidence that when teachers are engaging in these kinds of conversations, and we can document that they are doing that, one question you might ask yourself is, so what? And that can be answered at two levels. One so what is by looking at turn structure in conversations. And we can look at what is being said and the exchanges, what's being accomplished in interaction. And so basically we've done that. We have a paper in CDM about that, although CDM did not want to see the Jeffersonian transcription, and they didn't want to see the frame analysis a la Goffman. But that's okay. So, so that's one way of understanding, right, about what's going on when a person does this. You know, conducts one of these reviews or a formative assessment various opportunities in this, in what we're doing. But the other is that a lot of people say to us, is so what? You know, so the kids are thinking about statistics as measures. Well, if you have a measure that's sensitive to the kids' conceptions of statistics as a measure, then in fact you would expect to see a difference between students provided those learning opportunities versus students who were not. And so that's the notion of that.
I have a simple question. You probably think it's really simple. But I'm thinking back to your symbol of learning, assessment, instruction. And in your work, developing learning progressions of statistics, instruction obviously is a component. One of the variables is the teacher.
Yes.
And I'm interested in teacher education.
Yes.
So if you design a learning progression based on huge numbers of students, and you have the variable of the teacher, are there learning progressions of teachers? Would you say that?
Yeah,
or how do you,
I would, I guess.
How do you deal with that?
Well, that's the object of the changes in professional development around rehearsal of some of these practices of managing these kinds of ambitious instructional conversations. And I would say that our assessment friends originally thought that we would just get large samples. But the problem is that you can't measure something that doesn't exist. So, in fact, we had to change a lot of what we were about because they need large samples because their algorithms are greedy. So in essence, the program of professional development with the teachers came about as a result of that. And so there are many pieces to that. One is, as I said, the notion of managing an instructional conversation. The other is, well, what are we doing when we educate students about statistics? Right? I mean, what is that? What are they? What is variability? What does it mean to model? So we have to work these things through with the teachers. And then we have to think about how to communicate about prototypical patterns of student thinking. But what we try to do is have that communication, and then they try things out in classrooms, and they come back with parts of student work. So either responses to assessments, or just little clips from the classroom, or samples of student written work. And then we have conversations in our professional development sessions about those things, where they reveal about students, how might we promote student learning from whatever point they're at, and so on. And so I think unless you have, I mean, so I have designed documents about our professional development, because each thing we ask teachers to do has, of course, a rationale, and then forms of evidence about whether or not we think we're getting anywhere with them. So it seems to me that you have to at least have that in order to claim a learning progression, because otherwise I'm not actually sure what you're doing, in the sense that I think a learning progression is about a designed environment. So part of the designed environment is what's realized in interaction. And unfortunately, we don't really have great ways of talking about this, because interaction by its nature is contingent. And so the best we're doing, and I hope other people are doing better, is having prototypical forms of student response and so on. But the real work of teaching is how to manage that contingency. So what we're trying to do is provide examples and some tools to think with, and then trusting to developing professional practices, of which we understand some things, but not as much as we like. So I think that's a vital piece. And the other vital piece is you need forms of evidence. And if you want to play with people who are running accountability schemes, then you need psychometrically rigorous forms. I don't actually, it's not where my heart is. But the formative assessment is where my heart is. So the item has to be readable, the responses have to be readable in ways that are productive for learning. So some items are really good for this, and other items are not. So that's been part of the art form. And I'll give you the website, and you can go see if you think we've succeeded. So we have, part of the website are forms of student reasoning, and part of the website is formative assessment conversations in classrooms. So teachers can see the volley back and forth, and the juxtaposition of states of knowledge that we think are being revealed by student responses. And I think you have to have those things working in concert in order to have a learning progression. So I didn't really get to my conclusion. I meant to say that, I don't know how many of you have know the work of Peter Gallison? Okay, so that was a non-starter. Okay, this will not be a resource. He's a person who studies social practice of science, and one of his books is about studies of physicists. And physicists tend to segregate themselves into instrumentalists, experimentalists, and theorists. And the way the work of physics gets done is by establishing what he calls a trading zone. That is, the theorists speak in a language known only to the theorists, but it's partly intelligible to experimentalists and to instrumentalists. The instrumentalists know every darn thing there is to know about one of those counters. But the experimentalists need only the outputs of those things. They don't want to know about all those material constraints. And the theorists, they don't want to know about anything other than what's in their head. So he calls this confluence of communities a trading zone. And the notion of the trading zone is that they are places where these three communities meet to get the work of physics done. And the CERN system is a great example of that. Because I was talking to an instrumentalist just last week, and his view of what's going on with the magnets, it's just so much different than the experimentalist, which is so much different than the theorists. So what I'm saying is that in education, we actually have the same kinds of things going on. There are people like Mark Wilson, they really, 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 really care about variability and measure. And they spend their lives, there have been 3 innovations as a result of working with us that they've produced, coming out soon, I hope. And so they've modified their models because I am a pain in the neck. And so some of the questions we needed to have answered needed different models. Still hasn't done what I want them to do, but I'm still pushing on that. I want the stuff from the classroom into the models. And I know, yeah, it screws up the probability structures, but we need to get teacher judgment and student work into the formal systems. So they do that, and when they talk to us about the constructs, they have a vision of them, but it's not our vision of them. And we don't take these as learning ladders, right? We know that learning doesn't work this way. We take them as milestones and an outcome space in which we're going to make general progress, but there's going to be a lot of back and forth. Of course, duh. Okay, so that's called learning sciences. We know that. It's not reflected in that structure. For teachers, what the constructs seem to be doing is to put a mathematical horizon out there. And that's really important. We know that from the work of Derival and others. So for them, it's a different object. And for us, it's yet a third object. That's why we're spending a lot of time thinking about, well, which video and how to exemplify it, and what about interaction and so on. So this is the same object, except 3 very different views. So we coordinate with our colleagues. And so I'm not trying to diss anything they're doing, I'm just trying to say this is the reality. Okay? So when it comes to learning, when we talk to them, we would find some of their ideas about learning not all that complicated, let's put it that way. So we talk differently with them. They're brilliant people, it's just that they don't know a frame analysis from a turn-up for the most part. And when we talk about development of curriculum, I have someone working with me, Mayumi Shinohara, who was at West Ed for a while, and she's turned what for me were, well, let's see if I can find them. Well, that's the website. So, she's very good at thinking about how to structure curriculum materials in ways that are more intelligible to teachers. So that's another specialization. And, we have to meet in the middle. And this middle is what I think is called a learning progression. And it serves to coordinate the work of different communities, different goals around a common enterprise, just as it does in physics. So when you ask, is a learning progression valid, I would say, well, is it productive? Does it lead to new questions and new work in these different communities? And if the answer is no, then I'd say, well, you've done a nice piece of intellectual work, congratulations, but I'm not sure we want to spend this kind of resource and that it's important enough to spend this kind of effort. So while I think the idea of development is nothing new, and that's what some of us who started out thinking about learning progressions were just trying to communicate to our colleagues in assessment. That's where all this stuff came from originally. It's just an effort to say to them, we have to think about change over more extended periods of time. So I think that's where I'm at on learning progressions. And I don't think we should do this to everything. I think we need to pick things that we think will have high leverage, high payoff. For me, it's very clear. that you can't do science without this. You just can't. You can't do an experiment unless someone has carefully arranged everything for you. And if that's the kind of science you want to have, then basically you don't want kids to participate in science. You want them to participate in the products of science. I don't. So again, because education is a matter of values, we can argue about this for some time. But if you look at the new national standards, whenever they finally come out, practices of science are given pretty good status. Now we have to think about what we don't know enough about. What we're studying in our other work is how do these practices lead to generation of knowledge? How does generation of knowledge lead to changing practices? And what we're most interested in is measure and model, but you can think of others, of course. So that's where I'm at on this. And then if anyone wants more details about the psychometric models, etc., we can talk about them. But I'm just trying to say what the contribution is to the overall work.
Thank you very much. I think we're out of time. Just to a lot of the coding. Thank you very much.
All right, well, thank you.